This is Chapter 6, Ionic and Molecular Compounds, and in Section 4 we're going to be talking about polyatomic ions. So far all the ions that we've looked at have been individual single atoms that have either an excess of electrons or they're missing a few electrons, so they have a negative or a positive charge based on that. Now we're going to see how you can actually create a polyatomic ion, how a group of atoms, several atoms, can join together and they can covalently bond to one another in such a way that they end up with fewer or more electrons, and this gives the overall group a charge. Okay? These are called polyatomic ions. Poly means many, atomic is obviously atom, so these are ions made from many atoms. And some typical examples of these are CO3 2-, NO3-, and SO4 2-. We're going to learn all about those and the names for those and how they work when they are involved in ionic compounds. Most polyatomic ions consist of oxygen atoms bonded to another nonmetal, such as phosphorus, sulfur, carbon, or nitrogen. You can see the examples here, right? Carbon with some oxygen, nitrogen with some oxygen, sulfur with some oxygen. And we'll see many more examples. Okay? Usually they have a negative charge. Most of them have either a -1, -2, or -3 charge. The only real exception to that is the polyatomic ion that we call ammonium, NH4+, and that has a positive charge. Polyatomic ions are present in a wide variety of products and compounds and chemicals. So here, for example, you see a plaster cast, which has a regular monatomic calcium ion, but it's bonded to the polyatomic sulfate ion, SO4 2-. And you also have fertilizer here, which is a combination of two polyatomic ions, the positive ammonium ion, NH4+, and a negative nitrate ion, which is NO3-. Here we see a table with the most common polyatomic ions, and the particularly most common are highlighted in bold. So you can see here we have nitrate, chlorate, carbonate, sulfate, and phosphate. Okay? So typically the way that these ions were named is the original ion, whenever it was discovered, was given an ATE ending, right? As you can see, all the ones that I just highlighted have the ATE ending. And then if another ion was formed or was discovered from the same nonmetal bonded to a lower number of oxygens, then it would be given a similar name, but it would end in ITE. Okay? So nitrate has 3 oxygens, and then when an ion was found involving nitrogen and only 2 oxygens, it was called nitrite. Okay? Chlorate becomes chlorite when you lose an oxygen. Right, for carbonate, there's no carbonite, that's an exception. For sulfate, you have 4 oxygens in the original, and then if you have 1 fewer, that's 3 oxygens in sulfite, ITE. Phosphate also has 4 oxygens. Phosphite has 3 oxygens. Okay? So the ATE ending, unfortunately, it doesn't tell us exactly how many oxygens are in the ion. It's more of a historical oddity of how they were discovered or the process by which they were named. But we do know that the ions that end in ATE have more oxygen than the ions that end in ITE. But they tend to have the same charge. So nitrate and nitrite both have a -1 charge. Okay? Chlorate and chlorite both have a -1 charge. And in fact, chlorate and chlorite, you also have the perchlorate that has even more oxygens, but still a -1 charge, and hypochlorite, which has even fewer oxygens, but still a -1 charge, right? So these are all -1 charges. Carbonate has -2 charge. Again, we don't have a carbonite, but we have some other carbon-based ions in there that you can see. Sulfate and sulfite both have a -2 charge. Here and here, and phosphate has a -3, and so does phosphite. The other thing that you can note in here is sometimes an ion will have a hydrogen bonded to it. So if you take a carbonate ion, which is CO3 2-, and you bond an H+ ion to it, then the whole thing loses a negative charge. It becomes 1 more positive, so it goes from -2 to -1. Right, and you get the H in front. And so this is now called hydrogen carbonate, okay, or traditionally it used to be called bicarbonate. Same thing can happen with sulfate and sulfite. If you put a hydrogen on them, the charge goes from -2 up to -1, and you call it hydrogen sulfate, which is sometimes called bisulfate, or hydrogen sulfate, which is sometimes called bisulfite. Okay. Phosphate has a hydrogen phosphate that has one more positive charge, so -3 goes up to -2. And you can also add another hydrogen to phosphate, and you get dihydrogen phosphate, and so the charge goes up to -1. So these are the most common polyatomic ions: sulfate, SO4 2-, phosphate, PO4 3-, nitrate, NO3 1-, chlorate, ClO3 1-, and carbonate, CO3 2-. Okay, these are the most common, but not the only ones that you'll see in this course. When a related ion has less oxygen, like I said, you change the ending to ITE: sulfite, phosphite, nitrite, chlorite. Again, there's no carbonate. That's an exception. There are some other ions that don't follow these exact rules. So, for instance, we have the cyanide ion, which is Cn-. We have the hydroxide ion, which is OH-. And then we have the positive ammonium ion, which is NH3+. Okay? Keep in mind these IDE endings are similar to the endings for monatomic ions, but don't confuse cyanide and hydroxide with monatomic ions. These are polyatomic. So the IDE always means a negative ion, but typically it means a single atom ion, whereas for these two, they are polyatomic. And with ammonia, ammonium, right, you have the IUM ending, which is similar to the positive ions from metals. A lot of metals end in IUM. And then here we see also what I was saying about adding a hydrogen to an ion. You have carbonate, and when you add a hydrogen to it, you get hydrogen carbonate. Okay? Sulfate becomes hydrogen sulfate. And then here we can see chlorine really forms 4 polyatomic ions. This shows you the whole series of ions within a single nonmetal, from the one with the least number of oxygens to the one with the most number of oxygens. So hypo means lower, so hypochlorite has fewer oxygens than chlorite, and then chlorate, and then perchlorate has the most oxygens, ClO4-. But again, they all have a -1 charge. So how do we write the formula for a compound containing a polyatomic ion? Well, it's pretty simple. It's not too much different from the formulas for regular ionic compounds that we've learned. Okay? You still have to balance the charges, but now you're just balancing the charge between the positive ion and the total charge on the negative ion. So for instance, if you have magnesium nitrate, if someone tells you the name of a compound is magnesium nitrate, well, you know it has magnesium in it, and from its position on the periodic table, you should know that magnesium is always a +2 charge. Nitrate, here's where you just have to sort of memorize. Okay, you have to look at that table and commit some of those ions to memory, or consult that table when it comes time to do this, right? So nitrate is NO3, and it's very important to remember that nitrate always has a -1 charge. So if you are remembering or trying to memorize the table of polyatomic ions, you not only need to match the name to the formula, but the charge is also a crucial part of the formula. So nitrate has a -1 charge. If magnesium has a +2 charge, then we know, same as with our previous experience, that we're going to need 2 nitrates in order to balance that charge, right? The +2 here is balanced by 2 -1s from the nitrates. And so we have a single magnesium ion and 2 nitrate ions. The question then is how we write that, because if we just write magnesium NO3 and then put the 2 after it, it's easy to confuse that and make it look like it's NO32 or something like that. So if you want to indicate that you have 2 or more of a polyatomic ion, you need to add the parentheses around the polyatomic ion itself. Okay, so you can see that here. And then the 2, to indicate 2 of those, goes right outside the parentheses. So the 2 really means you have 2 of everything in the parentheses. You can think of it as a single nitrate ion, which is probably the more useful way to consider it, or you can look at it as a nitrogen bonded to 3 oxygens, which it is. And so if you have 2 of that, you actually have 2 nitrogens and 6 oxygens within this compound. Okay? But we don't typically think of them separate like that because nitrate is its own intact ion. So how do we write the formula for aluminum bicarbonate? Okay. Well, again, if we know the name, then it's really telling us the names of the individual ions. So we know we have the aluminum ion, and from its position on the periodic table, we should know that aluminum is always going to form +3 ions. It's in group 3A or 13. It has 3 valence electrons, and so it loses them to become Al3+. For bicarbonate, at this point, you might still need to refer to that table, look up the formula for the bicarbonate ion. If you remember it, though, it is carbonate, CO3, 2-, with an extra hydrogen. So you add the hydrogen in front, and then you bring the charge from -2, you add 1, and it becomes -1. So the bicarbonate ion has a -1 charge, and the formula is HCO3, -1. So in order to balance these two together, again, you can do it this way where you just think about the charges, or you can list the ions like I like to do. If you have aluminum 3+ and HCO3-, well, that's too much positive charge, so we can add another bicarbonate. Still too much positive charge, so add another bicarbonate. And at this point, we can see that now we have a -3 charge from the bicarbonate ions and a +3 from the aluminum, and so that's going to be balanced. So 1 aluminum will balance 3 bicarbonate ions. And so we write aluminum and then the bicarbonate ion formula in parentheses. Don't write the charge. Remember, you never write the charge of an ion in the compound formula, but you write the formula for the ion in parentheses, and then since we have 3 of them, you put a 3 outside the parentheses. So this is the formula for aluminum bicarbonate. Let's do another example. How do you write the formula for the compound called sodium phosphate? Well, to start with, you analyze the problem in terms of the name, right? The name tells you the names of the 2 ions involved. You have the sodium ion, that's the cation, written first, and the phosphate ion is the anion, that's written second. Okay? So identifying these, sodium on the periodic table is Na, that's the element symbol for sodium. And it's in group 1 of the periodic table, so it ends up with a +1 charge. Sodium has a +1 charge, always. Phosphate, you just have to remember, it's from that table previously in these slides, and phosphate is PO4, 3-. It's 1 phosphorus atom bonded to 4 oxygen atoms, and altogether they have a -3 charge. So now we need to balance them. Okay, here it shows you that you have 3 of the +1 ion, that gives you +3 on the positive side, and 1 of the -3 ion, that gives you -3 on the negative side, so that balances out to 0. If you want to look at it a little bit more visually, you can write the individual ions. You have sodium plus and phosphate, PO4, 3-. Clearly, this is too much negative charge. The phosphate charge outweighs the sodium charge. So we can add another sodium ion, but that's still not quite enough. We need to add a third sodium ion. Okay, and here now you can see that the 3 sodium ions add up to +3, whereas the single phosphate ion is -3. So these are balanced when you have 3 sodiums and 1 phosphate. Okay, 3 sodiums and 1 phosphate. The number in parentheses here and here are the charges. Okay, so now that we know how many of each we have, we can write the formula. Okay, you still write the cation, the metal, first, and so that's sodium, and it gets a subscript 3 because there are 3 of them. And then you write the formula for the polyatomic ion in this case, which is PO4. Okay? You don't write the charges for either of those. There's no superscript, no charges indicated in the formula. And PO4 can just be left as it is. You don't need parentheses because it's just a single PO4 ion. So, if you were to put parentheses like this, it's really unnecessary because there's no number going outside the parentheses. So you can forget about those. Okay? You only need the parentheses around the polyatomic ion if there's going to be 2 or more of them. Okay? And so this is the formula, Na3PO4. If we have the formula for an ionic compound containing a polyatomic ion, we also want to be able to translate that formula into the proper name. And the process is very similar to what it was before. You just need to identify the cation, and that's the first part of the name, and identify the anion, and that's the second part of the name. So in that regard, it's exactly the same as before. The only difference really is in identifying the polyatomic ion, which can sometimes be tricky. In this course, usually if you see more than one element in a compound, if you have 3 or more elements, that's a good indication that you're probably dealing with a polyatomic ion, okay? Especially if one of the elements is oxygen at the end, right? Most of the polyatomic ions are oxygen-containing ions, and so if you see some nonmetal followed by some number of oxygens, that's a good indication that you're looking at a polyatomic ion, and you should try and remember the table of formulas, right? You do have to be somewhat familiar with the table of formulas or have the table for reference. Okay, so in this first one, you have Na2SO4. The SO4 is a polyatomic ion. Okay. In the second one, it's FePO4, and here the PO4 is the polyatomic ion. In the last one, it's even a little bit easier to see because the polyatomic ion is set off in these parentheses. And it's in parentheses because there's 3 of them, indicated by this 3 outside of the parentheses. So whatever is inside the parentheses is likely a polyatomic ion. In this case, it's CO3. Okay. And once you've identified the polyatomic ion part of the formula, then whatever's left is the other ion. Typically, the polyatomic ion is going to be the anion, the negative ion. There's only the one exception of ammonia, right? NH4 plus is the one positive ion or cation that's polyatomic that we need to worry about. So the rest of these are going to be in place of the anion, which means whatever metal is also in the formula is the cation, or could possibly be this NH4 plus if you have that as well, but usually it'll be a metal. So in the first example here, it's a sodium. You have 2 sodium ions. Here it's an iron ion, and in the last one it's an aluminum. You have 2 aluminum ions. Okay, so we're going to do the first and the last one before we look at the middle one. The first one, if Na is the metal, that's sodium, and the name of this polyatomic ion, SO4, is sulfate. It's really SO4 2 minus. The 2 minus is why you need 2 sodiums to balance it out. But again, that doesn't take part in the name. That's not a part of the name because sodium and sulfate describes the structure perfectly fine. For the last one as well, you have Al, which is aluminum, and then the CO3 ion is carbonate. And again, CO3 is really CO3 2 minus, but the 2 minus is implied by the charge balance between an aluminum ion, which is always aluminum 3 plus, and the carbonate ion, which is 2 minus. So you don't need to indicate that in the name. For the middle one, however, there's a little bit of an issue because we're looking at iron. And iron is one of those transition elements. It's a metal that has a variable charge. It can form a few different ion types or a few different ions with different charges. So we need to figure out what charge it is in order to precisely specify which compound we're looking at. If we just say iron phosphate, right, because it's iron and the PO4 is the phosphate ion, that doesn't specify it well enough because there are a few different iron ions that could form compounds with phosphate, and we need to know which one we're talking about because they're different. So we do this by looking at the charge balance, okay, which means you need to know not only the name of the polyatomic ion, but the charge on it as well. So in this case, phosphate is PO4 and it has a 3 minus charge, okay. In this formula, you have one phosphate, right? There's no parentheses and no number outside the parentheses, so it's just one phosphate. And you also just have one iron ion. There's no number after the Fe, so it's only one iron. That means whatever negative charge the phosphate carries has to be exactly balanced by the positive charge on the iron. Since phosphate is -3, iron is going to be 3 plus. Okay? And so that means that the charge on the iron ion in this particular compound is iron 3. And so we again indicate the charge on the metal as a Roman numeral in parentheses. And this is just like we did previously. Again, there's no difference here. We're figuring out the charge on the transition metal based on knowing the charge of the anion. The only difference is this anion happens to be polyatomic. But as long as we know what the charge on it is, then we can figure out the charge on the positive ion. This is a table that shows several different ionic compounds, including polyatomic ions in their formula or in their structure. And it's not something that you need to memorize, but it does show you the wide variety of roles that these kinds of compounds play in our society. So ionic compounds, and in particular polyatomic ions, are pretty important for a wide variety of things. The other thing you could use this table for, if you want, is to just practice a little bit. So you can look at the formula in the first column, right, and try and figure out the name based on that formula. So here you have aluminum and a PO4, which is phosphate. Aluminum is +3, phosphate's -3. And so this is just called aluminum phosphate. Okay? Or you can look at the name in the right column and try and figure out the formula. Here you have calcium, which is 2 plus, and carbonate, which is CO3 2 minus. The 2 plus perfectly balances the 2 minus, and so you just have one of each, CaCO3. So you can do that and go through and use this to practice naming or writing the formulas for different polyatomic ion compounds. Let's do a few examples ourselves. Okay, so they're giving us names for different compounds, including polyatomic ions, and they want to know the formulas. So the first one is aluminum nitrate. Well, we know aluminum is Al, and if you look in the periodic table, it's in group 3A or 13. It has 3 valence electrons, and therefore it always forms +3 charge ions. Okay? Nitrate is in our table of polyatomic ions. It's NO3, and the nitrogen series of ions pretty much all have a -1 charge. Okay? At least the oxygen-containing nitrogen ions have a -1 charge. So if we want to balance the +3 in aluminum and the -1 in nitrate, well, we're going to need 3 nitrates. Right? Only when we get 3 nitrates will we have a -3 charge, which balances the +3 in aluminum. So we have aluminum and 3 nitrates, which is indicated by C. Okay? Al, and then in parentheses we have the formula for NO3 nitrate, and then outside the parentheses is the 3 to indicate that there are 3 of them. This first formula is not correct because there's no parentheses or number, so this implies only a single nitrate. This one is not correct because the 3 is outside the parentheses, but what's inside the parentheses is not nitrate, it's NO, and that is not even a polyatomic ion at all. It's in fact a regular covalent compound, so it doesn't belong here at all. So A and B are both out, C is the correct answer. For 2, we have copper 2 nitrate. Okay? And in this case, the Roman numeral, we have to remember, just tells us the charge on copper. So the formula or the symbol for copper is Cu, and the Roman numeral 2 tells us that it's Cu2 plus. Okay? You could also have copper 1, which would be just a 1 plus. In this case, it's Cu2 plus. And again, we have nitrate, which is same as in the first problem, NO3 with a minus charge. Okay? Let me erase some of this to make room. And so how do we balance them? Well, we have 2 plus from the copper and -1 from the nitrate, so we're going to need another nitrate to make it -2. That means we're going to have Cu and 2 nitrates, which is here, B. Again, this is just 1 nitrate, so that's no good. And this indicates 2 coppers and 1 nitrate. But 2 coppers would be +4, and 1 nitrate would be -1, which would leave this whole thing with a +3 charge. So it's not charge balanced, and so it can't be that. Okay, it's B. Question number 3 is iron 3 hydroxide. And again, iron we know is Fe, that's the symbol, and the Roman numeral 3 tells us that the charge is positive, Fe3+. Hydroxide is a polyatomic ion that we're going to become very familiar with later on in the course. For now, all you need to know about it is that it is OH, an oxygen bonded to a hydrogen, and it has a negative charge. If you want to balance 3 positives from the iron with a negative from the hydroxide, you're going to need 3 hydroxides. That means this is FeOH3. Okay? The 3 is outside the parentheses. The OH is inside. Here it looks like 3 irons and 1 hydroxide, which is not correct. Here it's just 1 of each, and that's not correct. Okay? And then the last one is tin 4 hydroxide. Tin 4 hydroxide. The chemical formula or the element symbol for tin is Sn. And tin, although it's not strictly speaking a transition element, is one of those post-transition elements that still has a variable charge. And so we can see the charge specified by the Roman numeral. It's a 4. IV is the Roman numeral for 4. And so this is tin 4+. Again, hydroxide is the same as in the previous example. That's OH-. Now we need to balance this single minus of the hydroxide against 4 positives. So we're going to need 4 hydroxide ions. And that makes this formula A. Tin hydroxide is SnOH4. Okay? When you say it, it's a little ambiguous because you can't indicate the parentheses. I guess you could say parentheses, but writing it down is more important. Okay? Being able to write down the correct formula. This is a useful flowchart for naming chemical compounds. We're only dealing with ionic compounds right now. We haven't gotten to covalent or molecular compounds yet, right? The molecular compounds are over here. So we're going to ignore this side of the chart for now. We'll come back to it after we finish that part of the chapter and we've learned how to name covalent or molecular compounds. We'll come back and see that. But for now, we start with the ionic side. We assume that we're looking at an ionic compound. Well, before that, how do we know if we're looking at an ionic compound? Well, in this course, any compound that includes a metal or the particular positive ion NH4 plus is an ionic compound. Okay, you need a positive and a negative in order for it to be ionic. So the positive charge is either going to come from a metal, a positive metal ion, or from NH4 plus, the ammonium ion. Okay, those are your only options. So once you see one of those, you know it's ionic. If you don't see either of those, then it is not ionic, and you'll have to wait until we learn about molecular compounds. Once you know for sure it's ionic, then it's just a matter of figuring out the names of the two different ions that are in it, right? You have the positive ion, which comes from the metal or ammonium, and then the anion, the nonmetal. Okay? So sticking with the metal side for a second, the first question you have to ask is the metal a main group metal? Does it only form one type of positive ion? Or is it a transition or post-transition metal where it forms more than one possible ion? If it just forms one type of ion, then you just give the cation name the name of the element, or it's also ammonia. Ammonia fits this as well because it's always +1, right? So the name of the element, calcium, lithium, magnesium, aluminum, things like that, main group elements. Okay? If it's a metal in the transition group or in the post-transition metals, then it forms more than one type of element, and you need to figure out how to determine the charge on it based on something in the problem, and then you'll write the name of the element followed by a Roman numeral in parentheses that equals the charge. Okay, so you need to remember the Roman numeral for here. How you find it will really depend on the problem. If you're given the formula, you look at the charge balance. Otherwise, if there's some other information, you might have to figure it out that way, or they'll sometimes just tell you what the charge is or which particular ion it is. But you do need to include the Roman numeral in order for this name to be correct. So that gives you your positive metal, right? It's only one of these two options. For the nonmetal anion, well, you have to figure out, is it a monatomic anion, just a single element, or is it a polyatomic anion? If it's a polyatomic anion, you just need to identify it from that list. Okay, try and memorize the list, and you'll be able to see which it is. You just use the name of the polyatomic ion. If it's a monatomic ion, you take the first syllable of the element name and you end it with IDE. So oxygen becomes oxide, nitrogen becomes nitride, on and on. Okay, and so that gives you your two ion names, and then you just put them together to name the compound. The cation name space the anion name. Okay, as long as you remember that the Roman numeral is part of the cation name if it's required, and you might need to know some polyatomic ions, then those are really the only tricks involved in naming ionic compounds. So let's take a look at these examples. We have two chemical formulas. The first is Ca, then parentheses NO3, and parentheses 2. Okay, so what that means is we have 2 of the NO3. NO3 is an ion, right? NO3 is the nitrate ion. It has a -1 charge. This is something, again, you just need to remember from the polyatomic ion table or look up in the polyatomic ion table. The other ion here is calcium, Ca. Calcium is a group 2 metal, and so it is always 2+. Okay? That means that we have calcium and nitrate. The calcium, again, is a main group metal, so we don't need a Roman numeral. So we can just call this calcium, and then the name of the anion, which is nitrate. And we're done. For B, for the second question, we have FePO4. So Fe is iron, but iron is a transition metal, so we need the charge on iron. We need some Roman numeral to indicate the charge. So I'm going to draw a question mark right now because we don't know which iron ion we're looking at. But we do know that the anion, the negative ion, is PO4. And PO4 is phosphate. And we need to remember from that chart that PO4, phosphate, always has a -3 charge. Okay? That's very important because without knowing the charge on phosphate, you'll never be able to figure out the charge on iron in this formula. Once you do know that it's -3, though, you have a single iron and a single phosphate, so the iron must balance it. So that means it's going to be iron 3 plus. Okay? And so that makes it iron Roman numeral 3, III. And so the name of this compound is iron 3, meaning the number 3 in Roman numerals in parentheses, phosphate. And that's your full name. Here you can see these steps laid out. Let's do a couple more examples. So in this one, you have Mg, which is magnesium. Magnesium is a main group element. It is not a transition element, so you don't need a Roman numeral. And you have the other ion, which is SO3, right? Once you know that there's a metal involved in the compound, then whatever is not the metal, you should understand is the ion. So even if you're not sure about your polyatomic ions, anything that's not magnesium is the ion in this compound. And so SO3 is the ion. SO3 is going to have a 2- charge, and it's called sulfite. It's like sulfate, which is SO4 2-, but it has one fewer oxygen atoms, and so it's sulfite with an I. The second one also has magnesium, right? Still don't need a Roman numeral because it's magnesium. It's always 2+. And SO4 is sulfate, like I just said. SO4 2- is sulfate. SO4 2- is the sulfate. So this is magnesium sulfate. In the last one, we have lead, but lead is one of those post-transition elements with a variable charge, so we need to figure out the charge. So we'll start writing the name with lead, right? But then we need a parentheses because we need to put some Roman numeral there. So let's look at the other ion to figure out the charge balance. Well, the other ion is PO3, and that is phosphite. PO3 3- is phosphite. But how many of those do we have? Well, according to this number outside the parentheses, we have 2 of them. That means that the total negative charge is -6. And so the total positive charge has to be +6, right? So the +6 from the leads doesn't mean that we have a lead +6, though. Why not? Well, because there are 3 leads. Here, there's a 3 after Pb, which means we have 3 ions of lead, and together all 3 of them add up to +6. So you have to distribute or divide that +6 evenly amongst the 3 ions, and so 6 divided by 3 is obviously +2. So this is going to be a +2 lead ion. Okay, so that makes this lead 2 phosphite is the name of PO3. Okay, lead 2 phosphite. Here you can see the answers. Now we'll do one more set of these. The first one is Fe2, and then in parentheses SO4. Outside the parentheses, we have a 3. So Fe2, SO4, 3. So we have iron, but we don't know the charge on iron. Okay, the charge is unknown. And we have sulfate, SO4, which we have to remember has a -2 charge. But we have 3 sulfates. So SO4 2-, SO4 2-, SO4 2-. That gives us a -6 charge. Okay? The iron, we actually have 2 irons. Okay? And so between the 2 irons, if it balances the -6, then it's got to be +6, which means each of these irons is iron +3. And so the name of this is iron 3, Roman numeral 3, sulfate. I'm going to write it down here. It should all be on one line, but run out of room. Okay? Iron 3 sulfate. In B, we have Ba3, PO3, 2. Okay? Ba is barium, and barium is always 2+. We have 3 bariums, so I'm just going to write 3 barium ions, just to make this explicit. It's not even really necessary, because you should know that PO3 is the phosphate ion with a -3 charge, and we have 2 of those, so PO3, 3-. So +2, +2, +2 gives you +6, -3, -3 gives you -6, and so that's why there are 3 bariums and 2 phosphites in this compound. Now, barium is always +2, so when we write the formula name, we don't need Roman numerals because it's a main group element. So it's just barium phosphite with ITE. The last one is NiCO3. Ni is nickel. It's a transition element, so we don't know what the charge is yet. But CO3 is carbonate. It's really CO3 2-. If you have one CO3 ion and one nickel ion, then the charges have to be equal and opposite. Carbonate is 2-, that means nickel will be 2+. Okay? And so this tells us the name is nickel 2, Roman numeral 2, carbonate. Okay? And here are the answers.